Twitch over there for those who are interested. So we'll get that going. And today is going to be relatively short. Well, yeah, certainly by other standards, short. And that's good news. I think it's good news. We're basically sort of ahead of track with regards to the material in the book and the presentations in the book and kind of where I was hoping to be at. And I'm not sure how everybody's doing with regards to how many people. I'm going to do a quick poll here. Have you done all the exercises through chapter 5? That's basically the question. In terms of has everyone... No? Okay, this is... All right, looks like... All right, so I don't want to get too far ahead. I don't want to start talking about models and objects and things too much until everybody's had a chance to kind of get texture mapping done. So I'm going to introduce something entirely different that is going to be hopefully sort of a bit of a backdrop for some other stuff potentially in the course. If you do look through the syllabus, the idea was that we would have some open room to talk about general graphics algorithms in addition to going, barreling through OpenGL, right? We don't want to kind of ignore the history. These days, it's sort of easy to say, well, okay, I don't have to worry about drawing lines. I don't need to know about how to draw pixels or rasterize things or draw a circle or do a flood fill or something like that because that's all done for me. If I'm using OpenGL, that's all. I don't have to actually draw a line. I just have to put geometry in, and boom, it happens. You just use draw lines. You just draw triangles and so on, and it will handle interpolation and all sorts of stuff to draw lines. And you just have to draw these do these wonderful shaders and calculate the geometry and so on. But you do get sort of out of the loop on that. So a lot of people kind of don't have to worry about the heavy lifting of rasterization. How do you actually get pixels at a specific location? How do you calculate that location? How do you, get the pixel on the screen where you want it? Because OpenGL does it for you. And so a lot of the time, there's a debate going on. Should we teach that? Should we teach these low level things? And I think it is important, especially because these algorithms that are used, things like Brezzenham's line algorithm, it's a classic, Brezzenham's line algorithm. I always get the pronunciation, I think, correct, but the spelling, half the time I get wrong. So Brezzenham, B-R-E-S-E-N, Brezzenham. And it's one of those things that's sort of like done to death. The moment you search Brezzenham's line generation algorithm or Brezzenham's line algorithm, you will find a million different versions of that particular algorithm. So let's do a quick poll. Heard of Brezzenham? Whoops, gotta get this right. Probably nobody. These days, you don't hear about them until you get to draw these wonderful lines. So it wasn't ancient history all that long ago, but until we had to actually draw lines, you could kind of like calculate exactly, an X and a Y position, and then say, okay, let me do some averaging and so on, and kind of take some time to actually draw these lines. And drawing lines on a computer was quite laborious, and it was kind of a pain because you'd have to calculate every value. And of course, when you're calculating a line, you're not going to come up with, wonderful integer-based numbers all the time. And, you have to worry about rounding. And what am I talking about? What does that mean? Okay. Before I go too far, let me show you a couple of quick examples of the issue that I'm talking about here. Why is it difficult to draw a line? You just have pixels. You just draw, dots on the screen. So let me switch over here to my other screen. And today's lecture is largely going to be inside of Visual Studio. So this is kind of sort of a show and tell. And what I'm hoping is to show you a couple of things that you will then potentially take on your own. Oh, you can't see stuff? Can you see? You can't see this on Twitch? Yes, I should be. So what's going on with Twitch? Oh, Twitch is probably good, but okay. Sorry. All right. Whew. I had Twitch streaming. I didn't have this going. It happens. Whew. All right. Better? The other part, didn't really care. I'll put up my slide if you like. Computer graphics, doing it the old-fashioned way. Brezzenham, etc., or et al., and others. Okay, so hopefully we're back on track there. That's a first. So let me get my... How's that? Better? Just so give me a... Okay now? Okay. Whew. All right. Thank you for pointing that out. I would have just kept going. Hopefully on Twitch things are okay. So, because that one definitely showed streaming. I'm so used to, anyway. All right, let's get back to it. So, computer graphics, doing it the old-fashioned way, Brezzenham et al. And et al. Means and others, et alia, right? Someday when you're doing lots of research papers and you have to do your bibliography and whatnot and all your footnotes, you'll run into et al. Quite a bit when you have too many authors and too many things who have contributed to the field that you don't want to list every one of them. So, okay, now getting back to things. Visual Studio. Yes, we're going to spend most of today's short lecture sort of in Visual Studio, and I wanted to sort of introduce some kind of old school things and show you some ways. If someone said, okay, let's do some graphics, but we're not going to use any graphics libraries, and we're not going to use OpenGL, and we're going to do it the most primitive way we possibly can. Let's try to do that. So let's come up with some ways to do that. And this is mostly a bit of a show and tell, and I want you to, at some point, try some of this. So I'm not saying this is a particular homework problem, but I'm assured that everybody wants me to, the other professors want me to make sure that you know about, Brezzenham and so on. So this is going to be the playground we can sort of do that in. So on the screen at the moment, you'll notice, and let's see, let me switch to a pointer here, I guess. I have a line. I drew a line. How exciting is that? But you'll notice that the line itself, this is a fairly low resolution image. I think it's 64 pixels by 64 pixels. And the line itself is not a wonderful straight diagonal line. Diagonal line would be kind of easy to do. So you'd imagine it would wind up being sort of a straight checkerboard, stair-step, diagonal, 1 pixel after another going diagonally. But the moment you're not perfectly diagonal or perfectly straight, you have to deal with these issues like, well, how do I deal with the rise and run and the pitch and the slope, of the line? And how do I figure out, at what point do I have these sort of stair step, how do I take care of these? You notice down here, it starts off, it's kind of, well, close enough to diagonal here, but then suddenly I know I have to go a little bit more from left to right rather than up down, and then here, okay, now I can go kind of diagonal and I have to do left right again because this is a slightly flat line at this point. Okay, so that's where Brezzenham's line algorithm comes in, and part of it also is like, well, we want to be able to do this relatively quickly. So for graphics, unless you want to really, really calculate everything out and you have all the time in the world, a lot of the time you're also thinking about efficiency, and so Brezzenham's line algorithm is largely a story also of how can we do something efficiently and avoid doing lots of divisions and so on and so on. Okay, so once upon a time, divisions were very expensive. Doing division was very expensive. And doing any sort of floating point math was also very expensive. So it's something we avoided a lot. And if you're trying to, implement something in as little silicon, as few transistors on a die as possible, well, you also do want to kind of avoid things like floating point divisions and so on and so on. So if you can do, simple integer operations, especially on something as repetitive as drawing lines, that's a good thing. So that's why Brezzenham is so famous. Subsequently, there's been other line algorithms that have come out as well. Wu's Anti-Aliased line algorithm. So are you at all, if I start throwing terms around such as aliasing, you should know a little bit about that from last time when we were talking about texturing. But what about anti-aliased lines? Does that, am I speaking a foreign language when I say, what is an anti-aliased line? Okay. So you've probably heard of them. Like in the case here, this is a very stark line. This is a very aliased image, right? It's very high contrast and everything, lines look ridiculously kind of crunchy and sharp here, right? One way I can smooth that out, and it's something that we have anti-aliasing in modern graphics as well, in modern graphics cards, because if I'm not careful, I wind up with these sort of sharp edges between different types of graphics. If I draw something and it has a pixel boundary, which obviously textures do, and even calculated things do, they're going to typically have boundaries like that. What I need to do is sort of smooth things out, and I might do that by kind of averaging across this line. And I might say, oh, okay, this pixel here shouldn't be full white, it should be a little bit gray, and this one should be a little bit gray to indicate that they are actually sort of on a boundary, right? So some things like that, right? So there are ways to make lines look smoother through these anti-aliasing, and Wu's algorithm is one of them. So I just want to mention some names. So Brezzenham and Wu with regards to their line algorithms. So what I wanted to do is talk about kind of creating a little playground. Since we're going kind of old school on this one, I set out this morning, literally a little while ago. I have to apologize. It's been a big week for games being handed in, and it's also, I'm sure, big for some of you who have been Game Dev 1 and other courses and so on, which is why maybe we need a little bit of a breath sometime. So I decided I would create, or kind of two parts to this assignment I gave myself before class today. And one was to try to implement the sort of the simplest image library output. I didn't want to use soil. I wanted to actually write a program that all it did was it would write pixels out to a file in some format that was basically sort of a raw image. So I was taking responsibility for writing pixels out. So I'm doing that with a file format called PPM, which is a portable pixel. What's the M part stand for? Now I'm forgetting it again. PPM file format is, if you go to Wikipedia, that sounds right. For portable pixel, or people are referring to it as portable pixel format, like the M is part of the format part. That's weird. It could be map though. I'm gonna, without stressing myself out too much, that makes perfect sense. I think map sounds better than matrix even. So, because after all, we were talking about bitmaps here. I'm just going to Wikipedia here. Let's see, PPM. PMP. It's not even in here? What happened here? It certainly is a format. PBM, which is portable bitmap file format, which is basically the same. So anyway, a PPM file, and there are programs that do open PPM files. So thankfully, that's not a format. I'm just entirely making up off the top of my head. Now, I might actually even go so far as if we could fake a PBM file, we might get a little bit more compatibility with certain applications. But I chose PPM because it is basically you write out a series of numbers as text for every pixel in your image. How much easier could that be, right? So let me show you. Let's see. Let's open up. Let's see if I can say open with, and let me open up this PPM file with Notepad. Oh, that's kind of fun. No, you know what? This PPM, part of it is human readable, but the rest is not. Which is fun. Let's not try to read that. But it's basically the simplest, one of the simplest file formats you can have. And if you look at the image here, or the code here, hopefully it'll make some simple sense here. This is really all there is to writing out a PPM file. Oh, was it someone have a question, or is that somebody's microphone? Maybe not. Okay. So PPM file, really easy to implement. It's basically, we just open a file and we can actually just do a stream out to the file. And the file header is really, really simple. It's basically nothing more contained in the header other than a header saying, yes, this is one of the files, and the dimension in terms of X and Y, and then a number delimiting the end of the header. Right? So we have a very, very, very simple file header for these files. And then we have three numbers, three characters, 0 to 256, that tell us the color at each particular pixel. Right? They're just streamed out to the file. And I have a simple for loop here, a nested for loop, once by one dimension and then the other dimension. So I have a J and Y, which is my, J and I, which correspond to my Y and X. So I can kind of run through the image and print it out. And I just output the pixel. And here I'm doing it monochrome to make it even easier. This is just a monochrome image because I don't have red, green, and blue. I just have the same number repeated. So I've now even watered it down one more and said, okay, I'm just going to do a simple monochrome image, and I'm just going to stream the output and then close the file. Boom, there's my image. And I can use, thankfully, I have Krita on my machine. I think Photoshop probably can open this as well. If you've never used Krita, you should check it out. It's a really great program. It's free, and it does pretty much just about anything you would want to do in Photoshop anyway. But there are other tools to do PPM files as well. But I give Krita a shout out for that. Okay, so here is my image file writer. First off, really, really, really simple. Okay, so again, going old school, going super simple. We did that, and all it's doing is saying, okay, take an array and write it out in this image file format. You'll notice I have foo here, which is just my array that happens to be a simple 64 by 64 array of characters. Okay, let's see, I think I declared it up here. So I have a character array of 64 by 64. So nice little bitmap. It's going to be a bitmap. I initialize that, again, going old school, just memset. I just give it a pointer. I tell it, okay, initialize all the values to be 0, and I tell it how big this area of memory is that I'm setting, in this case, to 0. So I turn my bitmap, or my potential, my array of pixels, I set them all to black. So now I have this little convenient 64 by 64 array that I can write pixels in. I can just use it. I can create my own bitmaps in there. So now I've got my playground for implementing crude algorithms if I want. And in this case, the first one I did was, of course, Brezzenham's line algorithm. And it's a simplified version. There are some weaknesses to Brezzenham's line algorithm when it comes to, what happens in various quadrants of the screen. If you're moving, lines in certain directions, they have certain slopes and there's certain optimizations you want to make. But here's a real kind of simple piece of it. And so what I've implemented, I've said, okay, I'm going to draw a line from 110 to 4848. So for now, let me go back, and without getting into the guts of it, I'm going to change this line to 114848, which should be a perfectly diagonal line. And save that. And you'll notice, yep, I'm not lying here. There's just Fstream and standard IO here, right? There's no other libraries. There's no graphics of anything going on in here. I feel like I'm doing a magic trick, and I'm explaining nothing up my sleeves. So I'll go ahead and I'll save that and run it. And over here, over in Krita, I'm going to just say, well, close the current one, and I'm going to open that PPM file. Again, you'll see a wonderful, perfectly diagonal line here from 11 to, what did I tell it? I told it to go to 4848, so not quite all the way down in my image. So I have a perfectly diagonal line, which now is nice and straight, and okay, as I move down the line, it gets 1 pixel per row and column, which is kind of awesome. All right. But in the case where it's not as simple as that, where I had before, say I went from 32.1, let's see if that'll work. Let's see if my algorithm is good enough to do 32.1 to 48.48. Again, I'll close and reopen here. And this is 32.1 to 48, 48. Nope, something definitely broke in my algorithm. Let's see. Which one did work? 40, 0, 110 did. All right. Let's try that one. This is what happens when you program right before class. So let's see. Whoops, cancel. Don't want to overwrite that. Close. No. All right, so that is working. Well, I'll have to do some debugging. And part of my goal today wasn't really to give you an exact algorithm for Brezzenham, because there's lots of Brezzenham algorithms out there, and what I'd like, the idea would be to take a look at a couple of them, how different people have implemented them, and kind of talk about really how Brezzenham works and why it's out in optimization. As you can see, there's no division in here, for example, and everything is based on integers in here as well, right? So how does that work? Well, let's see. This is one case where it'd be great to have a chalkboard, or maybe we'll even. I've been waiting for this day. Let's see if I can do this now. Okay. Hopefully you can see this. And well, the one bad part of this is gonna be my headset. Yes, I have a whiteboard. Let's see. Can everyone kind of see that? I don't know. Maybe if I keep the glare down a little bit, hopefully it'll be not too bad. Probably never try to do this again. So imagine that we had this line that we just did. Can you see that at all? Maybe not. Maybe this isn't a great idea. Yeah, today's that day. Today is that day. Let's go back here. All right. I'm just going to refer to this image, and it may require a little bit more imagination on your part. So imagine I were, you hopefully all are familiar with y equals mx plus b, sort of, it's easy enough to calculate a new position for a particular y value given the x value, and so on as you move across the image. So that's what, we start off with a typical y equals mx plus b, and we can kind of generate a line. Now imagine the real line in this case, and the real line would start, here at this brightest pixel here, and of course wind up at this brightest pixel here. And the perfect line would of course go from between one and the other. You know what? Actually, this is even better. Why didn't I think of this? I'm not sure it's going to let me draw wonderfully perfect lines, but perhaps here. So our perfect line would go straight through like that, sort of. And you can see that as it moves here and here and so on, where those are, it's that the line isn't passing through quite, it's the pixel as it passes through there, the choice of pixels that you have are further away, one is further away, one is closer to the line than the other. Right? In these cases, there's obviously a pixel that the center of the pixel and the line itself, they're very close. Right? So we start to get at these issues here where a calculated pixel, we have to decide which one is closer than the other. Was it in this case, we didn't continue with this pixel down here. We decided that the pixel here was actually closer to that line than the pixel down there would have been. Right? So what we can do to do that, and here's where my explanation. Let's see. Erase some of these. Is we effectively, throughout the algorithm, we're sort of just moving. Imagine we start off here. Whoops. Try that again. You know, we evaluate this pixel, and then we say, okay, now I want to, and there's an optimization that also happens depending on whether or not the you can figure out is the line longer in this dimension or longer in this dimension, so you can optimize, you know, how many steps you're going through. So we'll imagine in this case we're going to go, we'll run through it according to columns here. So we would say, okay, let's draw the next line and say, okay, let's evaluate potentially this pixel here next. And we'd say, okay, is the line, the destination above or below, you know, the real line here? If we had the option of a pixel here and a pixel here, if I evaluate the two of them and I look at the pitch, the difference between the two of them, is that difference positive or negative, indicating that it's above or below that line? Right? So we can calculate each's position and then use this idea of what's called a pitch, which is to say, okay, what is the relationship of that difference, you know, the two differences, to the line, to the ideal line, right? So we can say, okay, which one is effectively closer based on, you know, is one above or below the line? And if it's above, you choose this one. If it's below, you choose this one. And then we make the decision again as we kind of travel through, right? So it's always the optimization of even as Wu's algorithm comes in as well. It's always, you know, trying to figure out a simple integer-based formula, integer-based evaluation to say, okay, how far is an actual pixel location? This is where the rasterization piece comes in, right? We're basically evaluating at actual pixel locations and then making a decision as to, does that pixel get colored or not, based on some relationship to the actual geometry. Right? So that's sort of the fundamental idea, is that, you know, in the case of lines, we know that there's only certain pixels that we can draw, so we have to come up with some sort of relationship to say, okay, given a real bit of geometry, what should I put in that exact location? And in Wu's anti-aliasing algorithm, what it can do is say, okay, given these two pixels, which one is closer to the line? And so therefore you can calculate, okay, which one should be closer to the color of the actual line versus, you know, the relationship between that and the background. So you can say, well, if it doesn't actually straddle the line, then perhaps, you know, both of them need to be weighted towards the color of the background. Right? So most line drawing algorithms are going to get into that sort of situation. So let's see here. I think I don't have an example. I haven't implemented Wu's in here yet. Oh, let's see. I think I can find a simple example. You probably can find them also just, most of these are on Wikipedia, so kind of easy enough to find. Yeah, if you do simple search, you're going to wind up finding Xiaolin Wu's line algorithm. All right. Oops. Let me erase my fanciful artwork here. You can see once again, it says, okay, here's my target line, and I can compare the pixels that are nearest or that straddle that line to see, are they on the line, in which case the color of the pixel is weighted towards the actual color of the line. But if it's near enough, okay, then it's getting a certain amount of the line contributing to the color, but also a certain amount of the background contributing to the color, depending on how far the center of the pixel was from that line. Okay, so this is why this is cool. This one is more expensive calculation-wise, and it's slower calculation-wise, but it does a much better job of, you know, creating what look like, ultimately, if you zoomed out, that would look like a nice smooth line compared to the blocky lines that we get in with Brezzenham. Right. So what I'm going to leave with that one, or as part of the extra exercise that would love to leave for discussion, this is the open-ended part, is to say, okay, take the idea of a very, very simple bit or simple image library. So try to implement the ppm. If you want to go back and pause the video on that and see the ppm file, or even if you just Google for ppm, you will find I'm sure lots of different sorts of ppm libraries. And then also find a simple algorithm. It can be either it can be the Brezzenham line algorithm, or it could be Wu's algorithm. And okay, I was worried the water department's here. And try to implement them. Even if you are cutting and pasting code, it is quite interesting to say, all right, let's find the simplest one. How simply can we implement these, and then find one that works well. Okay, so it's really kind of a point for experimentation and interest. Your projects, you could choose to actually use a line algorithm or a fill algorithm, or some sort of rasterization to implement that, to create some sort of texture or something like that. If you want to use that as a foundation for texturing your objects and models and stuff in your real-time projects. But it's not an absolute requirement to implement this as part of a project. I would like to see you go through the exercise of doing it, right? So for one of the check-ins, at some point subsequently, would love to see, have you done something with a basic, abandon OpenGL, try to find a real primitive graphics library and draw some pixels, step through that same process. And if you want to go back and look at my example there, that would be good enough, right? So the idea is, we've all gone through the check-ins now, where we say, okay, let's look at the screen. Here's the image library that I grabbed. Here's a primitive rasterization algorithm that I found, and I got them working together, and kind of talk about kind of the general things of them. Okay, so take a little time to do that. And then I can check the box for primitive graphic primitives for you that are done by hand. All right. So the other thing I wanted to talk about today, with regards to some of the examples in the text for texturing. So let's talk about those. What I would hope that you would have mastered or been able to demonstrate, and one of the actual exercises from the book talks about this, but it didn't. I found what I thought was a better texture to sort of kind of lay this out and demonstrate it. So I'm going to recommend that you do the same. Let's see, which one did I modify here? I think I grabbed that one. So let me just run that one. Yeah. So, textured cubes. As you can see, there's myself and Ben floating around our cubes over here. This is a little bit of a take on the orbiting objects as well. And this is using a animated fragment shader, or a little bit of an animated fragment shader, using a textured cube here. But then also taking a texture that's not as simple as taking a square and just kind of mapping it to each side. And the purpose of this was really to show that you understand how to generate a simple UV map, that you understand the geometry behind the UV coordinate system. So one of the simplest ways to do that, arguably even simpler than the triangle, is really to just use some sort of dice or something like that. And if you Google, if you search on the internet, you can find lots of good examples of unfolded cubes that you can then use to texture a polygon, right? So you should, during the course of evaluating, once you get the basic stuff in the examples for exercise 5, try to expand beyond that and use some textures that you find on the internet and make sure that they map appropriately, right? Because it's easy, even in the case of just doing a crude mapping like the pictures here that I grabbed and put on the cubes. It'd be easy to not realize quite what's going on at some of the edges of those and so on, and how did they wrap around the cube? Did they really wrap correctly? Because ultimately, when you're in a game or in a program or something, you want it to be deliberate where your textures wind up. So do something that is kind of deliberately designed texture like that. All right. So, yeah, that's kind of what I wanted to throw out today. Just nothing. Well, I guess the idea behind the brute force stuff is new, but I'm not going to put I'm not going to stress anyone out and say, okay, we definitely want to talk about that. Code that up for next week. But at some point, I will consider that to be something we should be able to check in and talk through above and beyond just the straightforward stuff from the text. And eventually, what I'd like to do is, once I get my own feet under me a little bit more on some of those, is I'll provide some examples of other algorithms that you could also take a look at and so on. So maybe by the end of the semester, you might have sort of a collection of little toy algorithms that you've kind of put together that you can kind of refer to, and we can have that as another thing to refer to as above and beyond outside the other projects. Okay, I'm sure this is, today isn't my best day. Any questions on any of those things? I need to find where my other window went. Okay, here we go. Chat stuff. Okay. Meant to be non-stress day. But do you have any questions on that? I'm sure you will kind of solidify it as we go. Kind of refer back to this one. Take your time over the weekend. Worry about the basic texture mapping. Get that stuff done. Get chapter 5 done. And then we'll talk about the actual object loading and things next week as well, and kind of more dive into that. Is anyone still there? Am I still streaming? I'm not sure I see anyone responding. Okay. So, all right. Yeah, exactly. So today, what I would actually like to do, even with regards to, there's a good chunk of time left at this point. And quite honestly, the amount of time it would take, I give you two options to kind of, use the rest of the time in class today. And we will, because I think on Monday we also did, kind of real just text-based check-ins with a lot of people, because it was just kind of, Monday was crazy. So we're going to it's not Monday, excuse me, Tuesday was crazy, so we're going to step back a little bit. Use today in a open-ended, stress-free way to either, you have three choices really, go forward, work through the exercises and the text in chapter 5 with the texture mapping. Think about what your next project will be. And I threw some ideas there about, using IMGUI. That was another big, thing throughout there the other day. So if you want to do some research on IMGUI or try some things, with IMGUI, or if you want to just, try to grab a real simple PPM file generator and, create some arrays, and you want to just, have the experience of rasterization by hand, and you want to do that today. So leave those as three exercises, right? You should do all three of those at some point, but we'll use today as, take your choice of those three, and I will stop the stream, but remain on here and kind of circulate with people as necessary to answer any questions about that. Okay, definitely start thinking about the next project. I'd like you to, kind of be able to give me a one-liner at some point. You should already really by early next week have a concrete idea of what your next project should be. So be prepared if I ask anybody, if I just drop in on you and, sometime after the weekend, say, okay, what are you doing for project 2? Hopefully you have an idea and you can kind of just execute from there. All right, I'll do that. I'll stop streaming now. I think that's covered enough random fun. Today's the random day. Okay. I'll check in with people as we go. Thanks for your patience and accommodation today.